Well, this is a nice follow-on to the previous discussion. I'm here representing the Dawn team, and I'm very happy to be able to present some of the results relative to the organic material that we've discovered on Ceres. First, I'll give a very brief overview of background of the mission itself, and then summarize some of the initial results, and then get into the context of where we found these organics and what it implies for their origin. For those of you who are familiar with the Dawn mission, we launched a decade ago. We spent more than a year at Vesta, and now have spent 2 years orbiting Ceres. The two key instruments that are relevant to our discussion here are the visible and infrared spectrometer and the framing camera. Combined together allow us to not only identify the organics, but to look at the context in which they occur. The way Dawn operates and what the enabling technology for Dawn is, it's ion propulsion, which allows it to not only get from the Earth to the main belt asteroids, but also to go from Vesta to Ceres and to do all the kinds of things we've done in orbit. This is where we are. Of course, you know where Earth is, where Mars is. Vesta and Ceres both occur in the main belt asteroids. Vesta is more close to the inner part of the asteroid belt, whereas Ceres is towards the outer. And here we have some of the first results from the spectrometer. These were published in 2015, shown in black. The top spectrum is the kind of spectrum that we see everywhere across the surface of Ceres. Ceres is very dark, and shown in the top spectrum there, it's basically featureless throughout the visible until you get to about 3 microns. And then you start seeing a variety of features that are consistent across the entire body. There's a very prominent OH absorption. There's at 3.06 micron, a very prominent ammoniated absorption due to ammoniated phyllosilicates. And then there's a small amount of carbonates, and that's the basic structure of what we see everywhere across the surface. Recall, of course, that the surface has developed over billions of years, so it's a regolith that is a product of the basic content of Ceres. Everyone probably knows this bright spot in the middle of Ceres that everyone wants to know what it is. Last year, we were able to get some very good spectra for that. What's shown in red here, and it clearly indicates the presence of a carbonate as this primary material which was emplaced on the surface in this particular crater. And I give you the reference here. I'm not going to talk about that. What I do want to talk about is the feature that was discovered earlier this year in a very narrow zone on Ceres, which has all the other components, the hydroxyl, the ammoniated, but it also has a very distinctive 3.4 micron feature due to the organics present on the surface. And that's what I'll be talking about today. The original discovery paper was published in Science earlier this year. Shown here is some of the basic spectra. This 3.4 micron feature is at least as strong, and in some cases stronger, than the signature that is found in the most primitive meteorites, and shown in comparison here. Shown in the figure there is the distribution around one particular crater called Ernetet, but for those of you who have good eyes, you can see there's a lot of smaller areas around the area region that are also extremely important in terms of understanding where this material originated. And that's what we'll be talking about, looking at the remainder of the data this morning. First of all, for those of you who are not familiar with the spectroscopy, the diagnostic 3.4 micron feature is very diagnostic of the aliphatic, the long strings of organics. As you go from an aliphatic signature to the more aromatic, that feature, the 3.4, is less strong. However, coupled to the presence of the 3.4 micron feature, in the visible part of the spectrum, it's typically a very red-sloped spectrum. And this is the two parts of the spectrum that we have our instruments for. One instrument that measures the red or flatness of the visible part, and the near-infrared spectrometer, which identifies the diagnostic feature itself. And these two together help us look at the context in which these organics occur. Okay, here we go to the beginning of the crux of the data. Shown on your left here is the spectrometer is an imaging spectrometer, so each point you have a spectrum. And you see the image of this crater in the top, and in the bottom you see the strength of the 3.4 micron feature. Next to it is the camera, which measures the visible. It's at higher spatial resolution, but it can measure the red slope of the continuum. And you can see that they're directly correlated. So that allows you, when you know you have the organic species present, to be able to map and examine the context in great detail. Shown on the right are the spectra themselves, both in the visible part of the spectrum and the near-infrared. What's shown on the top of the near-infrared spectrum is a comparison of these organic-rich areas, shown in red, to the basic background Ceres, which contain all of these other absorptions, the OH and the ammoniated. But when you ratio the organic-rich area to the background, you can identify very clearly the organic species itself, independent of the remaining species that are present as well. Okay, this is the distribution of where we see the organic materials on Ceres, shown in red, and they occur in two types of forms. Centered on the crater Ernetet, labeled number 1, is not only small areas that are very discrete, and we'll look at them in closer detail, but also sort of a diffuse region of the signature. Scattered around it, across a 200-kilometer elongate area, are a lot of discrete areas that have the same signature. Further to the east and further to the west, and we'll look at 3 areas in particular, labeled 1, 2, 3, to look at the context in detail. And what I want to discuss with the people here is what is the origin of this organic material on Ceres. The team, as I'll close at the end, we don't have a full consensus. We have 2 hypotheses, and I've already learned there's a 3rd hypothesis here. First, let's look at the geology of the area. There's craters. It's a crater billion-year-old, several billion years of cratering history. Ernetet itself, which has this high concentration of organics, is a relatively old crater. It's still 1.5 gigayears old, based on the crater statistics. It does not have a coherent ejected deposit, whereas other areas, such as the area to the left, is a small crater that's only about 30 to 50 million years. We'll be looking at that one as well. It has its ejected deposit. So this is the overall context of the geology of the region. Okay, let's look in more detail at Ernetet, and this will be the first example we use. Shown on the left here is the crater in enhanced color, enhanced to show this red continuum, which we know now is associated with the organics present. Shown on the right are individual 7-point spectra obtained across the extended visible wavelengths. 4 of those areas are shown with the black arrows. There's one, the black spectrum is average Ceres, which is shown by this little box down here, and all of the red spectra are indicated with the numbered arrows. However, typically on Ceres, when you have a fresh crater and it exposes fresh material, they are relatively more blue than the normal background material, and we have an example of it even in the northern part of this crater here. So that's an overview of the Ernetet region, and we'll look at it more closely in the next several slides. We had a high-altitude orbit and a low-altitude orbit. This is the high-altitude orbit data for this crater Ernetet. Shown in the left is the brightness or albedo image. Shown in the middle is this color ratio, which shows you the distribution of this red material, which we now know is red organic-rich material. And shown on the right is basically a combination of those two, where the color ratio is shown in red, superimposed on the albedo. I personally find the middle one more easy to understand in a geologic context because it removes the topography and it lets you look at the distribution based principally on the spectral properties itself. Well, we'll look at these in more detail at the lower altitude data that we acquired. It's a little trickier to get good calibration, but gives you much more detail. And we'll look at both Ernetet and this area down near the bottom, Hakumy. Okay, first going to Ernetet. Here's the zeroing in, same kind of display, albedo, color ratio, and you can see the crater floor is itself heavily cratered. This is because it's an old crater. It has an extensive regolith development history, but superimposed on that, you can see this red area stretching across the floor. We'll look at this in greater detail, the middle image, which is the color ratio showing you the distribution of the red organic rich material. And you can see they're relatively discrete areas scattered across the floor. There's one area up in the top part of the crater, which is across one of the edges of a crater. This is not an artifact. It appears in additional independent data. We'll look at another image further south, which will include the lower part of this in independent data, but also includes the rim itself. That's what's shown here. And what's interesting on this is not only does it duplicate the floor material, but it also maps some of these very intense areas that go from the rim and into the southwest portion of the crater. Again, we'll look at these, the albedo and then the color ratio in higher detail. And what you see here, and these are the highest spatial resolution we currently have, which is 36 meters per pixel. And for those of you who have good eyes in the front, you might see those two spots that the arrows are pointing to are very small, very fresh craters. The size of these are only 3 to 6 pixels in diameter. And what that indicates is that this crater itself is on the order of 1 to 200 meters in diameter. Looking at the color ratio, again, you can see the same pattern on the floor material, very discrete areas, not directly associated with those older, larger craters, but sort of scattered in a linear fashion across. And again, these small craters that are incoherent material on the rim. Okay, let's go on to the next area. Okay, the Hakumy. This is one of my favorite areas. Again, the three kinds of displays. You see an older crater, you see a younger, fresh crater, which is only the 30 to 50 million year old crater, and what we call this lobate flow. On the left is the high altitude data. On the right is the low altitude data. We do not have it in color, but we do have it in albedo, so you can see the morphology in more detail. And what you see in terms of where this discrete red organic rich material is on in two locations. One sort of on a plateau on the edge of this large crater, as well as over on the side next to this lobate flow. Here's another image of the same area that sometimes is easier to see. Again, you have the two locations, one on this plateau in this 5-kilometer crater, but also on this lobate flow, which clearly it has, for those of you who are familiar with impacts, has the classic distribution of ejecta from an oblique impact associated with the exposure of this organic rich material. Okay, so we've looked at the Ernetet area, we've looked at the Hakumy area, and the Hakumy represents some of these very discrete areas, not a diffuse cloud the way the Ernetet is. We're going to look at one more area, the Umaga area, which is the furthest to the east. Here we have the Umaga region. The red arrows indicate the red organic rich materials. The blue arrows indicate the classic fresh material on Ceres. That has nothing to do with the organics. But this particular location shows that the organic rich material is distinctive from what is typically exposed by fresh exposures on the surface. Here's another view of the Umaga area in enhanced color and the color ratio. What you can see looking at the color ratio is not only do you have one small exposure that's very discrete in which the VIR instrument identified the 3.4 micron absorption, but you see sort of a trail heading off to the east as well. Okay, here's the overview. It's about a 200 kilometer by 100 kilometer region on Ceres that is the only there's one exception of a very small crater about 400 kilometers to the south, but this is the only region that we see this organic rich red material and its distribution both as diffuse as well as very discrete areas scattered across the surface. And as you can see in the description I've provided, these exposures are distinctly associated with very fresh, small craters, some of which are below the resolution of the instrument that we currently have. So, what are the properties of this red organic rich material? Well, it's closely tied to these recent small craters that are only hundreds of meters and smaller in diameter, and this implies that the organic rich material must be near the surface. And all of these are found in this one region. Yeah, okay. And most are discrete, some are diffuse. There's a possible directionality consistent with a field of secondary craters. However, there's no primary crater to be consistent with it. These are two end-membered ways of looking at this. Either they were formed, as was discussed previously, endogenically. The composition of Ceres and the evolution of Ceres could form organics in the interior, or they were brought to the surface from material in the solar system and deposit on the surface. Either one of these is consistent with the data that we currently see, but they are associated with these small, fresh craters. There's a number of mechanisms that could produce these in the endogenic. You need to be able to make the organics on Ceres. That most geochemists are fine with. However, and this is the problem, you need to be able to transport the material to the surface from the interior, and right now the geologic processes make that very difficult. So that's a problem with this. For the exogenic, the being brought to the surface, you need an extended source that passes through this part of the solar system, and most dynamicists who study how material moves in the solar system, it diffuses. It doesn't stay in a nice tight cluster. It would have to cover all of Ceres, not just a small region. So that's a bit of a problem. And also you have to preserve the organics during the placement process. Right now we have no unique smoking gun to determine which of these two processes. In talking to some of you over posters, there might be a third option, so I'd be eager to hear any additional options. The data that I presented here are in press, in maps, so you should be able to see it shortly as well. Regardless of which of these options or alternative options are proved to be the case, this red organic-rich material clearly exists in abundance in this region on Ceres, and it's clearly an important part in understanding and documenting organics in the solar system. Thank you.